Hey guys,
Hi guys.
this is Varsha and this is Devika. Say hi, Devika.
Hi Devika.
Yeah, and we are here presenting our screencast that is supposedly worth 2 of our multimedia things because it took us forever
to do.
Yes, we put a lot of effort in this, so I really hope you like it. So basically, we had a question.
Yes.
Yes.
It's the scale problem.
Yeah.
Which is basically, so we already know that scales, they show your weight when you step on
Yeah,
them.
which is like a force, right? So we were wondering, like, if you start walking on a scale, what's gonna happen?
Well, you might initially think, well, that's an easy question. It's obviously going to change. But as you look further into it,
We were thinking, why does it change, I mean, obviously you would think it was gonna change, but so we decided to see if we can predict using force diagrams if it was gonna change or not. So
Yes.
yeah, what we know, scales measure weight, not mass, and weight is a force in newtons, right? So so that was a good thing because it wouldn't just measure our mass, because our mass would definitely be the same the whole way, probably. Yeah. And then we also know that the whole Newton's third law states for each action there's an equal and opposite reaction, meaning the amount that you put onto the scale will push up back at you, right? So we made a force diagram. Behold my beautiful artwork. So this is Devika in 2 stages of her walking step.
Yes.
When you're normally walking. So we figured that in this leg over here would just have, a normal force and the force of the earth because it's just still while this leg over here is pushing off.
Right.
So it would be pushing in this direction, but the friction would be keeping it in place in this direction.
Are we allowed to say friction?
Yes, well, I mean the force of the surface on the foot.
Yes.
Yes.
Just pretend that it's not there.
Yeah, okay, sorry. This is supposed to be surface on foot. And then, of course, there's the normal force and the force of the earth. I mean, technically, this is pushing at a diagonal. And, so this is a component of the force, but either way, these two cancel each other out. That's why you don't slip around when you're here. And then there's the other one. When this foot swings around over here and is placing itself down, there's also the force in this direction, although it's a bit later than this step. When you're trying to bring this foot back over, this foot pushes a bit. So that's the force of the muscle in this direction, the force of the friction. At this point, this foot here is completely stagnant and it's just pressing down, and the earth is like the normal force is pressing up. So we tried to find where in this process does the mass change, not the mass, the mg, which is equal to.
Right. So
Yeah,
this is showing that obviously there's no change, so shouldn't the weight scale stay at the same
Yeah, it should stay the same. So, I mean, like, force of Earth 1 plus Earth 2 would be the girl's weight, Devika's weight, But, I mean, yeah, so it would be equal to mg. And the same thing here, these two added together should be mg. So,
right,
what happens,
That's kind of how we based our hypothesis that the scale should not move.
Yeah, it really shouldn't move due to all this stuff.
But we will
I
see
mean,
what happens.
Obviously, when you jump on a scale, it moves. So, what else is a possibility, Devika?
Let's check out the video that we made to
see if it does.
Yes.
I mean, we still think it will move, but we have no evidence backing it up.
So obviously
we are just kind of going to show you the video now. To see what was in the beginning.
Yes, there you go. It's good. Right. So
it's changing.
As you can see, as I step on it, it is changing.
It is changing. Why is it changing?
Obviously. So our force diagrams have failed us. There must be
failed us. What's going on?
There must be some more.
There must be other stuff.
Yes.
Why is there other stuff?
Right. So you get the idea of
You get
this.
yeah.
And back to our PowerPoint.
Which doesn't have much left.
Right. So here's our empty hypothesis and prediction.
Yeah, so we were going to explain this. So basically, we predicted initially, before we did any solid predicting, that the scale would change. But then we changed it once we did all of our force diagrams. So what assumptions did we make?
I guess we assumed that there's no instant force.
Well, yeah, I mean, what causes this? So we looked at other examples as well, like the whole spring scale thing. When Miss Bouget or Miss Resnick put the weight on the spring scale and moved it up and down with a constant velocity,
Right.
everything was just peachy keen, and there was no change in the force on the spring scale. But when she moved it at an acceleration or even a jerk, then the spring scale just sort of went crazy and just sort of started spinning around.
Right. So I guess that the reason our prediction after doing the force diagram was wrong was because it didn't account for the instantaneous walking.
So yeah, I mean, it was like there must be many different accelerations and velocities that, and I mean different balances of weight, and I mean maybe her center of gravity sort of shifts around as she sort of walks and tilts side to side, you know?
Right, right.
So probably there's a lot of acceleration and jerk going on there that sort of changes the weight on the thing. I mean, if you go back to the video, you can see that really doesn't change all that much. So
Right, it just stays between like
between like 59 and 60.
60-ish, right?
Yeah, 58 and 60 pretty much. So, yeah, so we have to take that into consideration. So,
Yeah, so that's kind of our.
so that's what happened. Yeah.
So I guess our conclusion is that readings on a scale change because, well, Newton's
Or
third law, but
yeah, so Newton's third law is basically just when a body is in constant motion or no motion at all, rather than just in an acceleration or anything above the acceleration. So that was our experiment.
yeah,
Yep.
and it kind of ties in what we learned about the force diagrams for walking and the third law and some things we haven't learned like the jerk and stuff like that.
Yep. So
Yeah,
Newton's third law lies when you're not in constant
velocity.
velocity.
Yeah,
It
pretty much.
lies to you. Yes. Have a good day.
Oh my gosh.
People, oh my god, there's no changing that. Alright, well, this was presentation. I hope you liked it. Yes.